standing on it. So what is the normal force really? Well, if we take our material and we use a scanning tunneling electron microscope, and we get to look at atoms, so we're now looking at individual atoms, there are surfaces of the materials that reflect the atoms. And when we look at the atoms very, very much close up, what we have are electrons, the electron clouds of these materials. And so what's happening at this particular point in time is we have a repulsion of these electrons, of those electrons, and back and forth. So we have an action and a reaction of the electrons in these materials. And so they're actually not touching. The electrons repel. And so in essence, every one of these electrons, they are floating and not in contact with each other. In that sense, then, whenever we have things in contact with each other, we have electron-electron repulsion. And there is actually no contact. All there is what appears to be contact at a macroscopic level. At a macroscopic level, there appears to be contact, but in reality, if we could get down at that level, there would not be contact. The electrons are repelling each other, and they are levitating. So in that sense, it is not possible for you to touch yourself. Take your finger and touch your cheek. What's happening, or your hand or your arm, and when you push, what's happening is the electrons in the cells and in the atoms that make up your cells are displacing those. And so what happens, you push to a point where you can push no longer. It's because your pain receptors are telling you not to push anymore because the cells and the nerves are being squished. But at all those squishes, what's happening is the cells are being pushed. The atoms are being pushed closer and closer to each other, which causes other things to displace. And so you might imagine then that if we had a very sharp object like this, say it was one atom, thick at the very edge like a knife, and let's say we had very strong bonding. When this knife point gets to here, well, what it will be able to do as that atom gets closer is the force of the blue on the knife atom, let me draw that a little more cleanly. The force of the knife atom and the material atom and the material atom on the knife will be stronger than the bond force holding the material together, and it will cause that bond to be torn. And so actually the knife cuts the material without it actually even touching. It's just about the electron repulsion. The electron repulsion here is greater than the bond strength, the force of the bonds here. And so it's able to push them apart. Now, of course, the flatter or the duller that knife is, the broader that surface is. And now when it comes into contact, there are multiple knife surfaces and there's much more force, bonding force holding the material together than that of the knife material bonding to the knife's ability to separate them. So in essence, that force that you're pushing and applying on the knife into the material is less than the bond strength of this material, so it doesn't cut. It's only when we're able to apply this force, these guys are more intact, the knife material is more intact, has stronger bonds than the bond strength of the material, that materials are cut. And so that's what the normal force is ultimately. Fundamentally, it's about electrons repelling each other. So now let's start looking at, as we're going to consider quite a number of cases. Let's take a look at forces here, and we're going to look at Newton's second law, which is F net equals ma. Now the net force is the sum of the forces. So the net force is the sum of the forces, and the net force is MA. And what we want to look at when we consider a case like a book on a table, like so. So there's my table. And we will place a book on top. Well, what happens with that book is there is a force of gravity pulling downward, and there is the force of the book, or the force normal, of the table on the book. Like so. Now, what we observe is the acceleration is 0. We observe no acceleration when we set that book on the table. That's an observation. The forces we have acting are the force of gravity and the force normal. Now, the force of gravity is the weight, which is mg, and the mass of the book is 2.6, and gravity is minus 10, so we get minus 26 newtons. So we have the force of gravity plus the force normal. So therefore, the force of gravity should be equal and opposite to the force normal. So we can see that. 0 force comes from the acceleration. The sum of the force is a listing of all the forces on the other side. And then solving, because the left side is 0, we get the weight is equal and opposite to the force normal. And the weight is minus 26. So the force normal must also be 26. And if we divide both sides by minus 1, we can see that the force normal is 26 newtons. Like so. Now I want to talk a little bit more abstractly about the forces. So we've got this weight that's 26 newtons. And when it's in contact with the floor, the table legs are holding up the weight of that table and the book. And so the weight of the table is 12.8 kilograms times 10, or minus 10, or minus 126 newtons. So that gives us a total of minus 152 newtons. So that 152 newtons is being supported by 4 legs. So 152 over 4 divided by 4 is 38 newtons. So a scale placed under each one of those legs is going to read 38 newtons. Just as if you had a mass of 100 kilograms and you stood on 2 scales, 1 foot on each scale, each one would read 50 newtons. This is how they weigh heavy trucks at truck weighing stations on the highway. The truck pulls up, they put a scale in front of each wheel, and they drive the truck up on it, and they add up the weight of all of those wheels, and that gives the total load of the truck. So now I want to talk a little bit about what happens on an even bigger scale. What is happening overall is that the book and the earth are attracted to each other. And that's what the force of gravity is. That is the action-reaction pair. We can look at the surface of the table and there's a normal force and the weight of gravity, equal and opposite at that point. And the reason that the book does not accelerate to the center of the earth or down to the earth is the table is in place. So what's happening is, not only is the earth pulling the table down, it's pulling the book down, so the gravity is pulling those two things down, but it stops there because there is the force of gravity, the weight on each leg, and a force normal of the ground pushing up on the weight of those legs. So each leg experiences a force normal of 38 newtons, and the downward force of gravity is minus 38 newtons. So in a very broad sense, we can look at the forces going on here at this particular location. We can look at the forces here, but what's driving this entire thing is the forces between the book and the earth. And we can view it like a sandwich. So lastly, I just want to go back to categorizing this force, normal force. Is it fundamental or derived? And the answer is derived. It is fundamentally electromagnetic. the repulsion of the electrons. Is it contact or at a distance? It is a contact force, and we want to specify macroscopically. And that's the perspective. If in doubt what the perspective is, always assume macroscopically what you see with your eyes. Most or very few, if any, physicists that you'll see in courses or even in college will be looking at an atomic or a molecular level. That's just a place I'm taking you to so you can really see what's going on. I find that exciting. It turns out it's actually at a distance at an atomic level. Is it conservative or non-conservative? I'm going to say that it's irrelevant because there's no work done by this force. So it's an irrelevant question, but if we had to choose, we would say it's non-conservative. In the next installment, we are going to take a look at the force of tension, both at a macroscopic and a microscopic level.